Viscereality, a bioresponsive VR system for breath-based interactions and coupled oscillator dynamics to augment altered states of consciousness. This project was made possible through financial support from the BAL Foundation and the Ernst Ludwig Ehrlich Study Foundation. Supporting institutions include the Qualia Research Institute, the University of Constance, the Max Planck Institute for Brain and Cognitive Sciences, and the Alias Research Network. We operationalize a breath tracking system based on a method from the VR application Flowborn, which leverages the controller's built-in positional tracking. By placing the controller on the abdomen, the system derives breathing patterns from spatial displacement and applies a movement filter to isolate respiratory motion. The algorithm then uses this filtered data to classify breathing states as exhale, pause, or inhale, enabling real-time breath detection without additional sensors. The breathing data drive a form of respiratory coupling in the interaction design, mapping changes in lung volume to the expansion and contraction of virtual space. Through this intuitive body mapping, the environment is intended to be perceived over time as an extension of the user's body schema rather than just as an environment controlled through breathing. In doing so, the interface aims to dissolve the boundary between internal bodily sensations and external visual perception through interoceptive-exteroceptive substitution. But, to evoke a realistic sense of spatial embodiment, the virtual environment must encode visual cues that support depth perception. Picture, if you will, a circle that gradually becomes smaller. You might see it as shrinking or as moving further away. This sense of depth comes from the way the human visual system uses changes in size, motion, and relationships between elements to interpret space. These effects are described by Gestalt principles. To name a few, the principle of good figure describes our tendency to perceive grouped elements as a single unified form. Similarity describes the grouping of elements that share visual characteristics. And symmetry describes the perception of shapes as unified when they are balanced and evenly arranged in a repeating pattern. Now let us review their implementation in VR from both a third-person and a first-person perspective. We implement these principles in a dynamic particle system that uses an icosphere distribution for uniform geodesic spacing, with particles expanding during inhalation and contracting during exhalation to provide spatially coherent depth cues that mirror the user's breathing rhythm. Building on this foundation, visual tracers embed depth perception directly into particle motion. These short-lived trails follow particle movement during sphere expansion and contraction, forming cone-like patterns that provide clear three-dimensional spatial references without relying on recognizable objects or semantic cues. On top of this, we apply continuous particle scaling to keep tracers visible throughout all breathing phases, including breath retention, ensuring they never become static. This persistent size fluctuation provides constant depth cues regardless of respiratory state, while also making the particles themselves appear more dynamic. Furthermore, we reinforce non-static behavior by adding structured noise, preventing the system from appearing rigid or predictable. This deliberate chaos later enables dynamic self-reorganization through coupled oscillator harmonics, allowing fluidity to arise from the interplay between disorder and structure. Building on this, surface wave oscillations generate continuous undulating, ripple-like motion across the particle sphere's surface, giving users the sensation of being surrounded by a malleable, elastic medium. This enhances the sense of responsiveness and plasticity as the environment appears to respond fluidly to the user's presence and breathing rhythm. Layered onto this, dynamic color integration adds visual complexity through unsynchronized chromatic cycles, introducing additional chaos into the system. This extra dimension increases the potential for pattern formation within apparent randomness while adding temporal depth, reinforcing the sense of continuous change. These conditions set the stage for synchronization mechanics to align color and motion into coherent patterns. Finally, coupling kernel synchronization brings oscillating particles into harmonic states during breath retention, when the particle sphere is neither expanding nor contracting. Our system coordinates motion, color, and oscillatory phase to produce coherent, symmetrical patterns in sharp contrast to the preceding chaotic dynamics. Designed to be perceptually rewarding, these configurations help users focus on the pauses between inhalation and exhalation, a subtle yet often overlooked aspect of breathing. By making these pauses more engaging, our system may support contemplative practices such as pranayama, box breathing, or resonance breathing, which emphasize breath retention. This approach also holds potential for clinical use, where fostering these breathing modes, whether for stress reduction, emotional regulation, or facilitating altered states, could be enhanced through our immersive, bioresponsive Viscereality system.